Good afternoon. Thanks for coming to our session. My name is Sangjin Lee. I work at Twitter. I'm here along with Lee from Hortonworks and Brushali from Twitter as well. So the title of today's session is Big Data Squared, How Yarn Timeline Service v2 Unlocks a 360-degree Platform Insights at Scale. Maybe the other one.
No, that's not.
Sorry, some technical difficulties here. Oh, okay, it went over.
Fine.
It just did.
The wrong remote.
Okay.
I did that. Sorry. Give me the other one. I don't want to leave it here.
Sorry about that. So let me just give you a brief outline of this session. So we're going to talk about why we need a timeline service v2. And we're going to go over some of the key highlights of a timeline service v2. And for your framework developers, how you can develop for it. And if you want to set it up, then how you can set up timeline service v2. And then we're going to talk about some key milestones of the development of timeline service v2. We're going to show you some cool demo also, and you can see how the whole thing really works in real. Okay, let me see a show of hands from you. How many of you are familiar with timeline service in general? Okay, I see about half. Okay, so in the interest of time, I'm not going to be able to delve too much into what timeline service is in general. So I would have to assume some amount of familiarity with timeline service. The V1 was released some time back, and it has gained some steady adoption out in the field, including things like Tez, Hive, Pig, and some MapReduce integration, and so on and so forth. And the community has been steadily improving timeline service v1. Recently, there was 1.5 release with the help of a lot of Yahoo folks, and there was some very nice enhancement done on timeline service v1. But still, we are facing some fairly fundamental challenges with timeline service v1. What are those challenges? The first challenge is with scalability and reliability. In the timeline service v1 architecture, there's basically a single instance of a timeline server that handles the entire cluster. It serves all the writes, it serves all the reads, and as you can imagine, as the size of your cluster grows, what happens is that basically it's not really able to keep up with the volume and the throughput that's thrown at it. Also, a related issue is that the storage is really a single instance of local level DB instance that's attached to the timeline server. And again, the same problem applies here. As the work increases, that single level DB is going to have increasingly more trouble keeping up with the traffic. And also there's a second issue of being able to keep all that data in the single instance. So it becomes pretty obvious after some size and after some time, it's going to meet a pretty serious challenge in terms of growth. And then there's a second issue of usability. At Twitter, we actually had an open source project called HRaven. HRaven is something pretty similar to timeline service and also a little bit similar to things like job history server. And what we learned as we interacted with our users is that people are not necessarily interested in dealing with all the individual Yarn applications as your units of understanding the work and the timeline metric. People are more interested in the higher level application that they wrote, and they wanted to attach metrics and values to that higher level thing rather than the individual Yarn applications that they see in the Yarn UI. So we're going to talk about the notion of flow in a minute. And And then also that there was a matter of metrics and configurations as first-class citizens. And we're going to go into a little more of that later too. And then we wanted to be able to roll up metrics happening down at the lower level entities like containers and applications, and being able to aggregate them up to a higher level entity so that you can get that aggregation really out of the box. And these are the things we wanted to really address with the Timeline Service v2. So this is a quick highlight of some of the things that we actually have been able to do. In V1, instead of a single writer-reader timeline server, we implemented a distributed writer or collector architecture. Instead of a single level DB storage, we went with a much more scalable storage based on HBase. In lieu of the first version of the entity model, we actually enhanced the entity model to address the earlier points I talked about. We also added the metrics aggregation as part of Timeline Service v2. And we also still provided a fairly rich REST API on top of all this. So let me go into the architecture a little bit first. So the very first thing we decided to do was we decided to separate the writers and the readers, because they follow very different traffic patterns, their needs are different, and their scalability needs are also very different. So we set aside the reader into its own component, and we have basically writers that are simply dedicated to handling the write volume that are coming in. And then the second point is, for the writer, we actually call them collectors in V2. We adopted a distributed collector architecture. And this is probably one of the more important points. Instead of having a single collector that handles all the write volume, we now have actually a number of collectors that are serving the writes. And one of the key decisions we made in terms of the design is to have one collector for each yarn application. We actually discussed many different options here. And for example, one of the options was to have one collector per worker node. That was another viable approach we discussed. But in the end, we decided on the approach of having one collector per application. And there are a few reasons for it. One of the reasons is that the intuition that there are probably fewer applications than the number of nodes in a typical average yarn cluster. So we don't have to spawn more collectors than needed. The second thing is also overall, this will result in fewer connections happening from the front end and also in the back end to the storage. And these connections will be much longer lived, because as long as that application is up and running, you basically have a stable connection happening from the application to the collector and to the back end storage. So this is the design choice we settled on, having one collector for each application. We still set aside one collector for the resource manager, because resource manager is really a separate source of information that still needs to write quite amount of data. And these distributed collectors will be discovered via RM, resource manager. And finally, we have a pluggable storage mechanism, but the default implementation is going to be HBase, and the implementation is actually provided out of the box. So this is the architecture diagram at a fairly high level, and this is probably one thing that you might want to take away from this talk. As you can see here, as an application master comes up in one of the worker nodes, we instantiate the associated timeline collector on the same node on which the application master is running. And from that point, the application master can start writing events and data to the timeline collector that's resident on that node. And it's going to write things like application-specific metrics and tons of other events. But the clients are not really limited to the same node. This particular application may have containers all over the cluster. And for those containers that are running on different nodes, the node manager that's hosting those containers can also write things like yarn container events and yarn system generic metrics and things like that, like CPU and memory, through the node manager, again, ending up at that collector that's sitting on the application master node. On the right is the resource manager and associated timeline collector. And there, it's dedicated to writing things like yarn application events and more important lifecycle events. And then the bottom here is really your timeline reader that's dedicated to serving timeline data to the end users for queries. This is a diagram that explains how the collector discovery mechanism works. And in the interest of time, I may have to skip this one, but I'm going to upload the deck later so you can take a look at this. Okay, let me talk about the new entity model a little bit. So the first thing we did was adding the notion of flows and flow runs as parents of yarn application entities. And I'm going to get into that really in a minute. The next thing we added was also we made configuration and metrics as the explicit top-level attributes of yarn entities. A third thing that we also focused on was we designed the system so that it can handle multi-cluster environment out of the box, from the storage to the reading layer, so that you can really have a multi-tenant or multi-cluster timeline service available in your environment. Okay, now let's talk about the flow. I talked about it a few times. This is time to explain what a flow is. In a nutshell, a flow is a group of yarn applications that are launched as part of a logical application. So if you think about concrete examples, it probably comes to you fairly easily. Think of your Uzi workflow. When you start an Uzi workflow, you usually end up spawning a whole bunch of individual yarn applications as a result. Or if you have a pick script or your scalding application, it ends up launching tons of little yarn applications, some in parallel, some in a serial fashion. It's going to create all those applications. But you usually think about the higher level thing as your application rather than the individual resulting yarn applications. Because the individual yarn applications may be really implementation detail in terms of how you complete your higher level thing. So this higher level thing is really the notion of a flow. Users are more interested in it, and also administrators, we are also more interested in that, because that gives you a much better way to associate value or cost associated with that particular thing. A flow has some key properties to it. The first is name. You usually have a name for your application, something like frequent visitor stats. That's very easy to understand. It may even be your top-level class for your scalding application. A flow also has a run ID. You usually run your application multiple times over, so that you want to associate each run, each actualization with a certain value. That's what run ID is about. You also want to version them. Let's say you had a pick script and you ran it for maybe 2 weeks, but you found a really nice improvement on your pick script. Then you change your pick script. Then you want to associate a different version with the change so that you can really see what change really introduced improvements or capacity improvements with those changes. So version is a fairly interesting and useful property that you can associate with a flow. So on the right side, I'm not sure if you can see it very well, but then basically we have a hierarchy of entities here. We can have containers at the very bottom, but their parents are yarn app attempts. Their parents are yarn applications. They can be now further grouped into flow runs, these individual runs that you have, and they can be also parented by a yarn flow entity. Let me talk about the configuration and metrics. So I said that now configuration and metrics are top-level attributes of yarn entities. What's now possible is you can do things like fine-grained updates on the configuration or metrics, and also you can do very sophisticated queries against configuration and metrics. You can do things like, give me all the entities where configuration key A has value B. And that's a pretty powerful thing you can do. Or you can do things like, I want to update on this entity, metric A, to value X. Then what happens under the covers is that only that particular metric will be updated, and nothing else about that entity will be touched. So you have a very small, fine-grained update happening on the storage. So from this entity container 1_1, I can simply update metric A to a different value, and not everything else stays exactly the same. Okay, at this point, I'd like to turn it over to my colleague Vrushali to talk more about the HBase storage and the things we did.
All right. Thank you, Sanjing. Hello. All right, so let's talk about the HBase storage and timeline service. We picked HBase to be the backend for timeline service, primarily because of its scalability. The row keys that we've designed are such that they allow us to do efficient range scans. So we always set a start row and, as far as possible, a stop row or a limit on our scan so that we retrieve only a limited amount of data. When we are creating the tables, we pre-split those regions in order to make sure writes are distributed across the HBase cluster. We are doing a filter push down as much as possible so that most of the filtering is done at the HBase side and only a limited amount of data is pulled back to the client. We are using a very cool feature in HBase called coprocessors. So coprocessors allow you to run custom code on the HBase servers, and we are using this for our flow level aggregation. I have a couple of slides coming up on that. We are also making use of cell tags in HBase. So these cell tags provide the metadata context to the coprocessor to allow it to do its aggregation operation. It tells it how to handle that data. We are generating custom cell timestamps. The reason being, we don't want two applications running at the same time, writing to the same column to overwrite each other whenever they're running as part of the same flow. So let us take a look at some of our tables in HBase. Let's go over each one of these. The flow run table. Like the name says, it stores information about a flow run. So several applications might run as part of one flow run. All of the information will get written to this table. The row keys here, now they are arranged as cluster, user, flow name, and inverted flow run ID. The exclamation mark is just a separator between the different row key components. Since HBase stores information in lexicographically sorted order, we use that to our advantage, and we invert the flow run ID. So what happens, the latest flow run will be stored first, because most of the times you're interested in the last n runs of a particular job. So all the runs of a flow will be co-located in HBase. All the flows run by a user are co-located, and everything for a cluster is, again, you'll get it as part of one scan. This is the table that has the coprocessor enabled on it. Okay. So the application table stores information about per application run. Everything that is run as part of one flow run will be co-located. Again, the most recently run flow will occur first. The same concept applies for the separator. The entity table, for all entities that are part of one application, they will be co-located in HBase. So here we have a slight change in the row key. We put the username first. The reason being, we want the writes to be as distributed as possible on the HBase cluster. So one user might be generating a lot of writes, another one may not be doing as much. We can control the pre-splits on this table better. All entity types are again co-located, so all the containers that are part of one application will be located together in HBase. The flow activity table shows you the activity on the cluster on a given day. It's primarily used to know, like what was running on the cluster last Thursday. You can find out. The app to flow table is a simple mapping table. Given an application ID, you can find out which flow it belongs to. All right. So metrics aggregation in timeline service is done at different levels. At the application level, we aggregate across the sub-application entities like different yarn containers and store it. This aggregation occurs in the collector's memory. So this is done in real time. So if you want to know for my application how many bytes were read by all the containers, this aggregation will tell you. Now across such applications, aggregation happens at the flow level. This is done by the HBase coprocessors. And across flows, maybe at the user level, queue level, or daily, weekly, any kind of periodic aggregation, that happens. And we plan to store that in Phoenix tables. Okay, so now let's take a closer look at how HBase coprocessors help us with the aggregation at the flow run level. So there's a lot going on in this diagram. So we have a timeline from T1 to T6 and going further. The blue boxes in this picture represent metric values from an application A, and the green boxes represent application B. Both are part of the same flow run. So let's say you ran a pig job and it created two applications and they are emitting metrics. The metrics that we are showing here are just belonging to the same metric, so like HDFS bytes read for applications A and B. Now over time, the counter value changes, so it keeps emitting more values for the same counter. Below the timeline, we are showing how cells are stored in HBase. So we are showing multiple cell versions for the same column. The bottommost row, the white boxes, those are the cells created by the coprocessor. Now, these are not yet stored back into HBase. So how does that happen? So let us say at time T4, you query for HDFS bytes read at the flow run level. Now, HBase has 4 cells stored for that column. So the coprocessor will intercept that get or scan call. It will create a custom scanner called as the flow scanner. So we've implemented our own scanner in order to look at the cells in HBase to handle those correctly. So the coprocessor looks through all the cells for a given column. It picks the latest cell per application because we want the latest metrics value for that particular metric. Now the application ID here is stored as part of the cell tags because this is happening in the context of the flow of the coprocessor. The writes are just coming in and they get written. The application writes are not affected by this. So the coprocessor will look through the cells. It picks the latest per application. Now what to do with that? What kind of an aggregation operation? It will again look at the cell tags. So this example shows summation, but we also have min, max, other aggregation operations. So it will add up the value and return, at T4 it returns 30. So when a flush call hits this table, the flush will clean out all the older values per application and keeps only the latest ones. Now let's say your applications are running and then they start completing. So the bold colored boxes in this diagram represent final values for the metrics. So an application is completed and you get a final value. Now, we don't want to keep storing multiple cells in HBase, right? So whenever a compaction call hits the table, the coprocessor will intercept it. Now it knows that applications have completed and enough time has gone by. So it will collapse those cells, collapse the final values, and create a new cell shown by the gray colored box at T12, and it will put that back into HBase. So over time, as applications in your flow complete, you will end up with just one cell for that column, and that will represent the aggregated metric value for that particular metric. And this is how we use coprocessors to do this aggregation. With that, I would like to invite Sunning back on to talk about the REST APIs.
Thank you. Okay, I'm going to switch to the reader API. I briefly talked about some of the things we can do with the reader API. The timeline service v2 REST URLs are under WS v2 timeline, surprise, surprise, instead of v1. We follow the pretty canonical REST style URLs, so you can pretty much imagine and follow what the semantics would look like. WSV2 timeline, start with the clusters and the cluster name, users, username, flows, flow name, runs, and run ID, and so on and so forth. And some of these path elements can be omitted if they can be inferred, and there are many ways this can happen. For example, if you provided an application ID, then we can actually infer a whole lot of information, so then you can omit some of these path elements to shorten the URLs. In addition, we also support a number of very interesting query parameters. I don't have to go through all of these things, but let me just quickly summarize what some of these things can do. Starting with something really basic like limiting the number of entities coming back, having a time range for the creation time. You can limit the fields that are coming back to you. You can say, I only want this specific metrics to come back to me, or configuration. You can set a limit of the number of metrics values coming back to you if it's a time series. So you can do a whole lot of interesting things with these query parameters. Or you can even filter by association. I want to just get entities that satisfy only this condition. You can create all kinds of filters based on the info, configuration, metrics, and events. And one nice thing on top is that you can even create more sophisticated, complex filters. You can have something like, give me things where metric 1 is equal to 50 and metric 2 is greater than 40, or metric 1 is less than 20. It's a very sophisticated expression now you can use to really telescope to the things you really want to get back. And these things are actually implemented as a predicate push down in HBase so that you really push it down all the way to the storage and to really optimize the data coming back to you. So if you're a framework developer that wants to integrate with Timeline Service v2, then how can you do this? It's still largely similar to what you would do with Timeline Service v1, but since we have a new entity API, you still would need to create a somewhat parallel code to Timeline Service v1 usage, and you probably find yourself having a switch so that you can switch between v1 usage and v2 usage. But the shape of the code is going to be fairly similar. You still instantiate the timeline client to write data, but you use the write method, the factory method, to instantiate the v2 timeline client. Now, one thing that's new with the timeline service v2 is because we have the distributed collector architecture, the address of the timeline writer is not hard-coded anymore. You have to discover it. That's the collector discovery part that I talked about earlier. So there are many ways of doing this, and one simple way is using the AM/RM client that sometimes you use with the application master. You say AM/RM client, you say register my timeline client, then RM will actually populate the collector address back to you so that you can start writing to that discover timeline collector. And from that point on, it looks largely the same. You just create the v2 entities now, and you populate the data that you want to associate. You only have to populate data that you want to update. You don't have to recreate the whole entity again. Then you call methods like put entities to write the data to the timeline storage. But that's not the end of the story. I told you about the flows, and flows is really this awesome thing. You want to be able to take advantage of the flow. Now, how do you do this? It's also pretty simple. All you need to do is provide the flow information in the form of the Yarn application tags. So until we have the explicit flow API in the Yarn itself, this is the mechanism that we're using. We also provide some utility methods so that you can easily generate these flow tags. So you can say, generate flow name tag, and you provide your own value for the flow name, and so on and so forth. And you simply add this Yarn tags to the application submission context, then you're in business. And then you can nicely group all your applications into the same flow, and you'll benefit from all the metric aggregation I told you about earlier. And if you want to set up this timeline service v2 cluster and start testing it, then how would you do this? Again, I won't belabor all the details here, but there are basically two major steps here. One is creating an HBase cluster for yourself. We're supporting version 1.1.x as the version of HBase. You set up the HBase cluster. You install the flow run coprocessor, and you can create the tables with, again, the utility that we provide for you. And then you can configure the Yarn cluster to, first of all, enable the timeline service v2 and add the HBase configuration so that your Yarn cluster can now start pointing to the HBase cluster you set up. OK, at this point, I'd like to turn it over to Lee, and he's going to cover the rest.
Thanks, Sanji. Well, so the first question I'm trying to address now is, where are we? We're currently hitting the alpha 1 mode for ATS timeline service v2, which means there are some discussion on merging those features, all of the features discussed previously. We're merging that back to trunk. And the discussion is ongoing, and we probably will start a vote very soon. So if you got any comments, any suggestions on this feature, just jump in the email thread and send the feedback to us. So right now, what we have is the complete end-to-end read-write flow. We got real-time and code processor aggregations. We got a new data model. We got the REST API. In general, we got everything. And we got some experimental integration with Yarn distributed shell and MapReduce so that we can test and make sure it works for ourselves. The next step, talking about future, is the second milestone, which is the alpha 2 mode, where we definitely want to attract some community attention and some ecosystem integration to integrate more frameworks with the ATS v2. At the same time, I'm not sure if any of you attend Wanda's talk yesterday about the new UI and Yarn scheduling. So we're aggressively integrating this with the new UI of Yarn. So after that will be the beta mode, where a lot of interesting things will happen, such as we freeze the API and we add security support. We try to launch containers as collectors as containers instead of a separate node manager auxiliary service for all of the timeline collectors. Probably we will do, not probably, but we'll do storage level for torrents so that there will be high availability for when the HBase storage is not available. So in general, the goal for the beta mode, probably happening later this year, is we try to make that production ready and migration ready. So with 5 minutes left, let me do a quick demo for what we have right now. As Sanjay said, there are 5 key features for ATS v2. One is scalability, like we generally have a new storage architecture. Second, we got HBase as the backend storage. On the usability side, the third thing is we have a new semantic as flows. The fourth thing, of course, is aggregation. And the fifth thing is we're trying to provide more query APIs, more reader APIs, so that users can easily query the timeline entities stored in this storage. So this is a brief integration with the new UI of Yarn, with a probably older version of the UI web page. But here we introduced the full activity page, where all of those things are backed by an HBase cluster. I deployed it locally. So that's the HBase storage. And then showing flow semantics here, I created one customized flow. That's my first flow in the cluster, and I've got several flow runs for this flow inside the cluster. Clicking into each of the flow run, I've got a set of applications. All of those applications serves as the component of this specific flow run. So in this, we were organizing all of the applications together, and I clearly know what is the goal of this sequence of applications and what exact applications are inside. So those are the flows. But inside the flows, we're doing the aggregations. As I click through the run ID for each of the flow runs, I'm aggregating for memory. For example here, this is a pretty cool sunburst chart. This is the overall usage of memory for this specific flow run. And we can see there are several applications. As you can see here, there are several applications that taking the memory for this specific flow run. Inside each of the applications, we're aggregating for different containers. You can see the memory usage among different applications. They're pretty equal, but inside each of the applications, the containers are using very different memory. So those are the those are the metric aggregations. And because we support very cool filter system, right now, what I can query is something like this. I can query for all of the containers within one application that use more than 20% of the CPU. So I can craft this REST URL call, and I can return all of the containers for their detailed metrics for memory and CPU. Right now, the main filter predicate is on CPU. So I'm filtering all of the containers for the CPU usage that is greater than 20%. So together, we're putting all of the container information because we have the new storage architecture. We can store this amount of data, and we can do some very cool filtering. You can filter on metrics. You can also filter on configs, like what about all of the applications with metrics, some metric greater than some value. So you can do all of these tricks. So that's all of the demo, and can you switch back to the slide? The last but the least thing is we want to say thank you. So this is a joint community work that includes several different parties. So I would like to thank our active contributors to this project, Jinping and Vinod, also with me from Hortonworks, Varun and Naga from Huawei, Sanjin, Rashali, and Yoop from Twitter, and Jijie, who joined Facebook during his working on this project. So thank you very much. Also, the HBase and Phoenix community provided tons of help on our integration. So thank you very much. So this concludes the talk, and thank you for attending this. And we definitely want your feedback. So thank you.
If there's any questions,
Yeah, just come up to us. We got 30 seconds left.
unless you're hungry.
Yeah. Sure, yeah.
Yes. Okay.
You
Logs.
Any plans to handle the logs?
Log aggregation is a different story, but I'm pretty sure it's also happening in Yarn. So it's
So we don't really
Yes.
store.
So the question is whether we have a plan to handle the log aggregation as part of the timeline service.
Yeah.
Currently, we don't have that plan, but it's something that we could look into in the future. But log aggregation itself is a fairly
it's happening.
big thing, and for the interest of the scope, we haven't really done it.
Okay. Actually, our time is up.
Yes.
Okay, we'd be happy to talk.
Yeah, let's talk afterwards.
Yeah, thank you.
Thank you.
No, thank you.